Cambridge Lab, UK. So Christopher is the head of research software engineering and the University of Cambridge, co-director of the Institute of Computing for Climate Science, and active principal software engineer in the Cambridge Open Zettascale Lab. He has been involved in high-performance computing since last millennium, when he's sysadmin at Crate T3E. I don't know, many of you young people may not have heard of this system. Since then, he has worked with HPC systems in the area of climate science in several national research institutes, helping researchers get the most out of this large. So he will be today talking about MVAPICH at the Cambridge Open Zettascale. So let's welcome Chris. Go ahead.
So, hello. Thank you, Dr. Panda, for the introduction and also for the invitation to talk here. And that was mainly as a result of the collaboration between the OSU, the research group here, and the Cambridge Zettascale Lab. So I'm going to explain both of those things in the slides. My name is Chris Edsall, as said, Head of Research Software Engineering. I'm going to start the outside and work in. So the Cambridge I'm talking about is the one in the UK, not the one in Massachusetts. It's a very old university there, coming up on 900 years, and with a very large research focus, very strong in technical areas. And as a result, graduates of the university have spun out lots of companies in the various tech fields, in IT, in health sciences, in all sorts of areas around the local regions. So if you look at the breakdown of the contribution to the UK economy from various regions, the region we're in, Cambridge, provides the highest, and a lot of that is to do with the so-called Silicon Fen. If you're not aware of a fen, it's a sort of marshland. So it's very flat. We don't have a valley there, but in Cambridge we have a Silicon Fen. The university itself, by several rankings in the top several, sometimes we're number one, sometimes we're number three, depending on what you're looking at. A large number of Nobel Prizes. I think I'm not going to go through all the items on the infographic there, but Cambridge is reasonably impressive within the UK academic system and also in the global academic community. Inside Cambridge, we have, like most universities do, an IT service, and inside the IT service sits research computing services, and that's where I am, my team is, and we provide the operational HPC facilities for, I think, as it says on the slide, both researchers within the university and also national services through various different routes. We have a community called DIRAC for astrophysics and theoretical physics. We have an open call system via our funders, UKRI, for access to HPC resources at large scale, and we provide some of that. We also have users from industry, as described on the previous two slides. The area around Cambridge, we've got a lot of people doing CFD, a lot of people doing life sciences, and we also have some commercial activities where we partner with Dell and provide consultation for Dell customers. So our system isn't as prosaically named as Owens or Pitzer or any of the ones at OSU. It's got an acronym. It's the Cambridge System for Data-Driven Discovery, which is so long I usually say CSD3. It's made up of different partitions of systems. I've left some of them off, so we've got some Skylakes, but we don't talk about those anymore. We've got a large number of Cascade Lakes and Ice Lakes. These aren't the sort of final figures. These are, I just looked yesterday and that's what we had. We've got more in the pipeline coming online soon. And as Gilad said in his presentation yesterday, we've got Wilks 3, that's what we're calling the GPU partition. So we've got 80 nodes with 4x100 of the A100, the large memory version. Those nodes have ConnectX 6 as the NIC, and they also have one Bluefield DPU per each of those nodes. One of the things we did in RCS is set up with our partners this thing called the Zettascale lab. And this is actually a slide from ISC earlier this year. This is Jeff he's not on this. I didn't have the Jeff McVeigh one. It's from Jeff McVeigh's keynote, where he announced that we were changing our name from the Zettascale lab. Since Zettascale's done now, we've got one Zettascale system on the top 500 list, so proof by existence. And so we're setting our sights on the next goalpost, which is 1,000 times or 1,024. Yeah, 1,000 times bigger at Zettascale. There are a lot of people in the community who think it might be a little bit too soon to start talking about Zettascale, particularly on the time frame that some of the time frames that have been proposed. But if you don't start looking at it now, suddenly the hardware will arrive, and we won't be ready to take advantage of it because we won't have thought of all of the things that are going to go wrong, that are going to need to be worked on and fixed between now and when we can make advantage of Zettascale systems. So on the left of that slide, sorry, on your right, my left of that slide, those are the people who are involved in the Zettascale lab. So Dell and Intel providing a lot of the hardware, and Dirac, as I mentioned, that's the astrophysics, theoretical physics community. UKRI are the large funding agency in the UK, and UK AEA are the civilian atomic agency. They're looking at fusion. And so we've got a confluence of HPC hardware expertise, integration expertise, and users with use cases that we expect would require at least exascale and as much computing as we can provide. Within the Zettascale lab, we're looking at these particular areas. I mean, there's all sorts of things you could choose to look at, and we've decided to focus on these 7. Energy efficient computing. I was fascinated by Martin's slides at the end of his talk on the power use in different phases of or different MPI calls. That's the sort of thing we are looking at. We've been doing some work on power management on GPUs, using static power management. We're now looking at active power management with Intel's GOPM software. If you have a Zettascale system, you're probably going to produce a zettabyte of data. No one can look at a table of that and get insight from it. So we're going to need to improve the tools we use to handle these large volumes of data. In particular, visualization. You're not going to be able to dump a zettabyte of data to disk and then post-process it to get your image. You're going to have to be doing some in situ visualization. So that's a theme we're looking at. Relevant to today's talk, to the MUG conference, we're looking at what the interconnects could be that you would use on a Zettascale system. The programming models is taken care of in the One API Center of Excellence. So we're looking at things like SYCL and for Fortran OpenMP offloading. The cloud native supercomputer, as Gilad said, we have that as one of our themes. So we work with a local small medium enterprise called Stack HPC. They have a product called Scientific OpenStack, and we use that to integrate the systems. As since this is the first MUG back in person after the pandemic, we're sort of aware of emergencies that can happen that can need large amounts of computing on short notice. so for epidemic modeling, for drug discovery, etc. And finally, although CPUs and GPUs and network cards are interesting parts of an HPC system, if you neglect the storage, you're not going to get the performance either. So we need to look at storage systems. So those are the things we're going to be working on over the next couple of years. I don't know, it just went, and the mic's gone. Yeah. Oh. Yeah. There we go, thank you. So, why am I here? Because we've got a collaboration with Dr. Panda's group. If you look at the MPIs that are involved, MVAPICH is clearly a very important one for high performance. And Dr. Panda has been working with the University of Cambridge for some time now, going back to our earliest GPU system, Wilkes-1. And what we're doing now, now that we have the Zettascale lab to sort of host it, and we've got staff that we're employing in the Zettascale lab to do the work, we're looking at increasing the number of things the number of activities we collaborate on. And so I had hoped to present a whole bunch of results today, but we only started this sort of increased pace of work a few months ago. So what I'm presenting is the caveat is this is very much a work in progress. And it's just a teaser, a few of the things we've been doing. Is it Amir and who else? Moshi from Broadcom earlier on in the conference both put out a plea for more automation of benchmarking systems for reproducibility. And so that's one of the things we're doing. So Stack HPC, who I mentioned earlier, started this work, and we've been carrying it on. And it's basically combining a couple of tools from the open source HPC community, SPAC, which we'll hear about after the coffee break, so I won't steal too much thunder. But the idea is that is a way of building application software deterministically, so that you can sort of record all of the dependencies that went into an application. And Reframe is a regression testing framework which is ideally suited to high-performance computing systems. So what we do is we clone the Reframe repository and we add a few things to it for making sure that the graphs are automated. So essentially, it's a push-button process now. If you have a new target, so there's a new partition on your HPC system, or a new NIC you're looking at, or a new MPI library, it's very little configuration to add that into the system, and also it's one button to push to run the tests, which sort of eliminates a lot of the human error that comes into when you've got a large number of configurations to take care of. The benchmarks that we're looking at, a combination of synthetics and applications. It's a growing list of applications. The synthetics is obviously the OSU micro benchmarks. And I say I wasn't not really involved in this. It's the work of my colleague Casper Cornett in the Zettascale lab, and here Mustafa. What we've been doing just recently, we've had access to some of Intel's Ethernet 8100 series cards, the Columbiaville NICs, which work at 100 gigabits per second. We've been testing them with one Dell Internet switch. You might say this doesn't look like Zettascale, and you'd be right. The aim of this piece of work is it possible to make a small workgroup server, workgroup cluster, 32, 64 nodes, something that'll fit inside one switch with Ethernet. So obviously, InfiniBand would be ideal, but is Ethernet okay? And so that's what we're looking at here. One thing to note, if you do have those Intel NICs, they use PSM3, so you need the MVAPICH 3. We used the PSM3 that came with the Intel Ethernet Fabric suite. There is apparently also one in the latest Intel MPI. And so you get the familiar looking graphs for bandwidth and latency. The blue line is InfiniBand, obviously better, but we get similar latencies to InfiniBand at large message size and similar bandwidth to InfiniBand at large message size. There is a environment variable you can tweak for the rendezvous threshold size for on the Intel case that makes the right-hand graph a bit smoother. The reason we've got the unsmooth version is it's not currently the default, and so Intel are looking at possibly making that the default and further in later release of the software. For applications, although it says MBIME, this is actually the motorbike test case. This is a bit small, so we've got super linear speed up on the InfiniBand and Intel out to 16 nodes. The advice here is the 20 million cell case scales better at higher node count. And that's a similar, we've got CP2K here, which is material science code. I was going to talk about the test case. There we go for GROMACS. So it's similar to OpenFOAM in that so we've got test cases increasing in size, going from left to right, and the Ethernet works okay at largish node counts with large work group size large, largish node count and largest test case size. The next thing we're going to look at is the DPU, the collectives. So there was some interesting looking performance graphs shown earlier in the conference on other material science codes. I think it was VASP. So there's a material science code that we're interested in at Cambridge called CASTEP. It's one of the top 5 codes on our national system, Archer 2, by usage. Spends 30% of its wall time waiting on all-to-wall communications. And so that looks like it would be an ideal case to try and improve the performance. The colleague in my team who's working on this, Arian Tamaris, said that to achieve the overlapping of the communication and computation would need changing one of the key data structures in the code. And so unfortunately that sort of flows through all of the code. It's a reasonably invasive change. So he said we wouldn't be able to get results in time for MUG, but that's something we would be looking at. And also trying to find other codes with a similar sort of FFT opportunity, should we say. Another thing we've been looking at is the big data features that are in the MVAPICH releases, in particular the MPI for DASC. So this is the work of my colleague Stephanie and also Amir here. And what we've done, we looked at both CPU and GPU. So for the CPUs, we're using MVAPICH 2.237. For the GPUs, MVAPICH 2 GDR. This is essentially the next steps on the slide are in the release notes. So this is, as I said, the work in progress. First thing we want to do is make sure that we've installed the software properly and that it's working properly. So we use the test cases, the NumPy sum, and on the GPUs, the CuPy sum. So that's that's a small number. Each of those workers, this is CPUs, that's probably nodes. And so this is a fragment of Python code taking some random numbers in the matrix and adding it to its transpose and distributing that computation across a number of worker nodes. The default communication is the green bars there, which is TCP, and with MVAPICH on CPUs, we get the blue bar there for wall clock time, lower is better. And on GPUs, again, this is the matrix plus the matrix transpose of a whole bunch of random numbers and distributed in this case across each worker here is a GPU. So that's actually less than 2 nodes of the A100 nodes because we've got four GPUs per node. And so the good news is this is showing the right figures. So that's a good start. The next thing is to scale it up. So we've got a larger system to run it on. And then after that, to find some applications. So we're talking to some people in climate, the people at NCAS, National Centre for Atmospheric Science at Reading, part of the Excalibur project. They may have some climate cases for DASC, in the first instance, not GPUs. We're also talking to our friends at the Square Kilometre Array, and they do have a DASC GPU case, something called Rascal, which we might look at to see if the MVAPICH library can speed that up. So, in summary, we've set up the Zettascale lab to look at the challenges around the next generation of supercomputers. We've started this collaboration with OSU, and as we bring more people into the lab, staffed up fully, we hope to have a lot more of those work streams addressing those 7 themes that I talked about earlier. And if you are interested, those are our URLs. Zettascale Lab, you can email us at info@cosl@hpc.cam.ac.uk. We have a Twitter account at Zettascale Lab, and the bottom 2 are my contact details. So with that, I will take questions.
Any questions locally or from remote?
Harry.
I had a quick question. So can you go back a couple of slides with the DASC results? Yeah, the next one. So in some cases, MPI seems to be performing better than MPI no GDR. Did you guys get a chance to figure out why that was so?
Unfortunately, no. August is a terrible time to try and do things because everybody's on leave. And so the person who did this work, Stephanie, was on leave this week, so I can't ask. So I don't know the answer to that question. That's something to look at. So what have we got on? And you're looking at worker count 4 and 6. So,
yeah, 4 and 6 is along the lines of what I would expect. But 1, 2, 3, and 5, they kind of look like interesting anomalies that I want to figure out what is going on. Thank you.
I will go and I'll take that as something to look at next week. Yeah.
Yep.
Thanks.
Any other questions? Okay, so if not, let's thank again Chris. We'll take a break now, coffee break, and we'll come back at 11.